I will be talking about explicit solutions to some particular equations from mathematical physics. It's joint work with my colleague Sergei Shindin from University of KwaZulu-Natal and my PhD student David Sipoka. Let me change the view. Screen. Let us do something like that. Okay, following the suggestions by Ivan, let me introduce the University of Pretoria. So it is slightly older than University of Ljubljana. We had 114th birthday just now. So this is the oldest building, existing building of the university, going back to 1910. This is one of the newest. And this is the Department of Mathematics here at the bottom. So this is the largest stationary university in South Africa with about 46,000 students. Okay. Let me start with the quotation, which in some sense make me very proud of working in fragmentation and coagulation problems. So coagulation and fragmentation belong to the most fundamental processes occurring in animate and inanimate matter. They describe events ranging from social and animal groupings, phytoplankton aggregation, blood agglutination, droplet formation, solid drugs breakup, and so on and so on. And therefore, together with the Boltzmann equation that describes collision phenomena in rarefied gases, the Navier-Stokes and Euler equations modeling the flow of fluids, the coagulation fragmentation equation in its original form going back to Smoluchowski, and describing rearrangement of particles is considered to be one of the most fundamental equations of the classical description of matter. So this is quite important class of equations. And just to tell you something about the processes. If we are looking at pure fragmentation and coagulation, so we can imagine molecules or clusters consisting of some basic building blocks. And such a cluster like here can split into two clusters. For example, here, this triplet gets detached and this quadruplet gets detached from this cluster. But at the same time, one of these subclusters can get attached to another cluster, forming a bigger cluster. So this is fragmentation and coagulation process. Original equations in such a case where there are basic building blocks of molecules were formulated by Marian Smoluchowski in the case of pure coagulation case in 1916, 1917. And they were generalized to coagulation and fragmentation equations by Becker and Doring and Blatz and Tobolsky a little bit later. However, in many applications, it makes sense to consider a continuous size variable X and as the only variable required to differentiate between the reacting particles. And in this case, forgetting about coagulation, we obtain the fragmentation equation, which is the integral partial differential equation, non-local, linear, of type 1. So what we have here is that U, the unknown function, is the density of particles of size X. So roughly speaking, the number of particles of a given size. A describes the rate at which the particles split into smaller pieces. And then the integral part tells us how many new particles of size X can appear after fragmentation of a particle, of course, of a larger size. So here we have the number of particles of size Y, which is necessarily bigger than X. Then each particle of size Y splits into, let us say, B particles of size X, and this happens at the rate A. And these two must balance, so the rate of change of the number of particles in the system is the balance of these two mutually opposite processes. Because we are talking only about rearrangement of particles, we must have something which is called local conservation of mass, which is expressed by equation number 3. Namely, if you have parent of size Y and it splits into certain amount of particles of size x, then these numbers multiplied by masses of particles put together must again give you the size of the parent particle. So this is local conservation of mass. So as I said earlier, equation number 3 states that fragmentation is just a rearrangement of mass, and the total mass should be therefore conserved. If you formally integrate, the equation, indeed you will find that the total mass of the system defined by this integral is constant. However, despite apparent simplicity, this fragmentation equation in the linear, even in the linear case, presents a lot of challenges. Namely, we have something which is called phase transitions. In fragmentation context, it's called shattering, and you can find, just going quickly through these examples, you can find coefficients, rate coefficients, which produce a solution in which the mass is constantly decreasing. So the mass is leaking from the system. So it is something like in the Markov processes theory is called explosive Markov transitions. So essentially probability is leaking out of the system. We have also multiple solutions of various sorts. So if you simply look at the original equation, which I wrote earlier, this one, if you simply try to solve it, then you are never sure that you will be getting a correct solution, the proper physically relevant solutions. And for example, this simple version of the equation has at least 3 formal solutions. So functions which substitute into the equation will give you 0, give you identity. And this is actually where I stopped with semi-group theory. To understand what happens, you really need proper functional analysis background here, and you really need solid semi-group theory. In particular, this middle equation, this middle solution, U2, is the solution, the semi-group solution, the solution of the problem provided by the semi-group theory. However, my talk is not about semi-groups here, but essentially about trying to find explicit solutions of equations, because this is what engineers are interested in. And in fact, actually, the motivation for this work, for this paper, is that I got invitation to submit a paper for 70th birthday of one of the towering figure in the field, Robert Ziff, who in some sense reintroduced fragmentations in the 80s and gave a number of very interesting results, formal results, but they are still actually fueling the development of the theory of early semi-group theory. So as we know, engineers are interested in situations which are computable. So they are not interested in abstract general coefficients, and in fragmentation coagulation problems, they are mostly interested in the so-called power law coefficients. So everything is essentially in the form of monomial or polynomial. So in this case, the fragmentation rate is given by the power of x. The distribution of daughter particles is also given by sort of like a monomial type of equation. And in this case, if we substitute these 2 formulas to the equation for fragmentation, we obtain integral differential equation of the form 12. And probably the first person who found the solution of this equation was Filipov in the 60s. Filipov wrote a very seminal paper on fragmentation problems, but because of course it was early 60s and he wrote in Russian, the paper was never really distributed in the West. And in some sense, Ziff in the 80s recovered a lot of results coming from the early Filipov paper. But it turns out that you can actually reduce equation 12. This is coming from the paper by McGrady and Ziv. McGrady was a PhD student of Ziv in the 80s. I mean, it's not too difficult to observe that essentially you can use integrating factor, which reduces this system to a slightly simpler equation. And what they did is they simply applied the power series expansion to 13 and arrived at the explicit formula given by, I think it's called Kummer hypergeometric function of the second kind, or something like that. I'm not good in special functions, but it's actually so the tabulated special function. And this was more or less the end of the story for pure fragmentation equation. It's maybe useful to remember the equation. It is just time derivative of the unknown equal to the integral of the unknown function, in some sense like convolution with exponential function, because we will see this equation a few times later. Now, in many applications, both in engineering and also in life sciences, fragmentation can occur alongside other processes. So what can, for example, happen is process of, if you have a cluster of cells, for example, phytoplankton cluster, we may observe that a cell inside will divide, split into two cells, and, for example, this cluster, because of the splitting, will, because of the division of this cell, which was sort of like bridging these two blue and red clusters, the cluster will split, but contrary to the previous case, the total sum of the total size of the system will be bigger than at the beginning. Yes, because you have one more cell here coming from the division. So you have an example of fragmentation with growth, with birth process. In engineering applications, the same process can occur, for example, when you have sort of like molecules in some solute, and you have deposition of matter from the solute onto the surface of the molecules. And we can observe, of course, a converse process in which this cell, which bridges, combines or joins these two separate subclusters, simply evaporates. So, for example, it can enter into some chemical reaction and be dissolved into the solute, or, for example, if you are talking about cells, it can die. And then we observe that a single cluster of size 7 will split into two clusters of total size 6. So you have fragmentation with loss of mass. If you want to write down the equation for this system, we'll see an equation which is very similar to what we have seen a few times before. Sorry. So essentially, in the second line of this equation, we have what we had before. So this is fragmentation equation, fragmentation term. But here we have plus or minus first order term, which describes either the growth, in the case when we have plus here, the growth of clusters, or the decay of clusters if we have minus. I think that in the talk of Marta Tyran-Kamińska today, we had terms of this type. So mathematically, all these equations are relatively close to each other. Now, we can first try to simplify this equation just to get rid of unnecessary parameters. I mean, at this moment, it doesn't look too be too much simpler, but essentially what we are after here is we don't want arbitrary power multiplying Q here. So that's why we simply consider x to the power alpha as z, and therefore this main term here is linear. And then you can see that the integral operators here, I will explain why they are two now, are free of the kernel. So they are essentially, they are simple integrals. And they are, unfortunately, this single integral operator splits into two cases, because if alpha is positive, then this transformation changes semi-infinite interval 0 infinity into 0 infinity. But if alpha is negative, there is a converse. So 0 infinity becomes infinity 0. And therefore, the integration from x to infinity in the second case becomes the integration from 0 to z. So depending on the sign of alpha here, this integral operator becomes either the integral from z to infinity, or the integral from 0 to z. And then you have definitions of coefficients which are not important for general from the general point of view. So this is what I explained right now, that if alpha is smaller than 0, then the roles of plus and minus here in this equation become reversed. So the growth becomes the decay, and the decay becomes the growth. We will denote by j plus and j minus the integral operators which appear here. And this is important because they are nothing but antiderivatives. So in some sense, we managed to convert a complicated fragmentation operator into something which essentially involves only antiderivatives. Now, equation 16 is still very unpleasant because it still has first order term, transport term, and the non-local integral terms. In the 90s, it was a very bold idea in two papers by also engineers, Huang, Edwards, and Levin, to simply use the characteristics. I mean, you have first order equation, so why not use characteristic transformation and see what happens? So they used characteristics, and they transformed this equation and were able to get closed form solution only in one particular case, namely when here this coefficient mu became 0. So essentially you have constant coefficient here, and also when they didn't have this term here. So they were able actually to convert this problem in this case to the equation which I showed you some time ago, namely to equation number 13. The reason why this idea doesn't always work is that to use the characteristic method, we must know that the characteristics which we build are filling the whole quadrant z bigger than 0 and t bigger than 0. So because, I mean, the whole problem is posed in the first quadrant. In the decay case, where they were able to got the closed form solution, this is fine. But if you consider the growth case, then the problem requires the boundary conditions. The other problem is unfortunately that if you change the system into characteristic coordinates, then the system becomes non-autonomous. I looked at this paper when we started actually working on this problem, and we realized that actually there are two other cases or three other cases which can give us solutions, explicit solutions. First of all, if we look at this problem and if we assume that mu is equal to 1, so if you have a linear growth case or linear decay case, it is a very important case in biological applications because typically the rate of growth of a cluster is proportional to its size, because each cell inside the cluster has the same probability of growing. So the more cells inside the cluster, the faster they grow. And in the first approximation, you have proportionality here. And this is a good thing because in this case, the characteristics are given by exponential functions, and they all, in both cases, growth and decay cases, they fill the first quadrant, and they don't require any boundary condition. So we don't have to impose any additional conditions for the transform equation. And if we make a few changes, actually, this is, I mean, in looking for explicit solutions, usually you try a number of approaches, and sometimes you are lucky, sometimes you are not. So in this case, you make, I don't want to go through details, but in this case, we make the transformation of coordinates. We change time. So we replace time by exponential time, and we use the integrating factor. And after this, we obtain equation 18, which is time derivative of the unknown solution, coefficient times either the integral from x or from xi to infinity or from 0 to xi of the unknown function times the exponential. Convolution is exponential. Exactly the same as in the case of pure fragmentation. So we have transformed yet another equation into the same form as the originally, as it was originally done by Ziff and McGrady. If we consider constant growth and decay, so if we assume in our model equation here that this coefficient is, sorry, this parameter mu is 0, this is the case which was dealt by Huang, Edwards, and Levin. So if mu is 0, then if you look at the right-hand side, then unfortunately we see that we have to impose another condition on theta. So theta must be here 0, otherwise we have a singularity here, which we, at this moment, we don't want this singularity. So we impose these two assumptions now. In this case, the characteristics are easier linear functions, but the problem is that if we are dealing with the decay case, the characteristics are like on the right-hand side, so they fill the whole quadrant. But if we look at the characteristics for the growth case, you can see that the characteristics starting from this line are only filling a quarter of the quadrant, sorry, half of the quadrant, and the other characteristics must be somehow determined by boundary conditions, which must be imposed on the system. We impose the boundary condition simply that the solution at z equal to 0 is 0. And there are several cases. I don't want to go into details into these cases, but they are essentially some decay cases become growth cases and so on. But whatever you do, in the characteristic in the characteristic coordinates, we obtain the equation similar to the transformation, to the classical pure fragmentation equation, but as I said earlier, with non-autonomous coefficients. Here we have time dependence. But the problem is now that in the characteristic coordinates, we obtain a boundary condition along this black line here. So we have to not only to solve the integral differential equation of this type, but also we have actually to impose boundary, to make this solution subject to a boundary condition. So the original boundary at z equal to 0 becomes this line here. I don't know, there could be several ways of dealing with this problem. What we did, we assumed, that we know the initial condition on the whole real line. This is something which sometimes is referred to as Kelvin method of images. So we will be simply looking for a solution for a missing part of the initial condition. So we know the initial condition at for psi bigger than 0. We know this, but we extend the known initial condition to psi smaller than 0 by 0 and introduce an unknown boundary condition psi, which we assume to be 0 for psi bigger than 0. And this psi must be determined for psi smaller than 0. And for such an extended solution, we require that at this line here, the solution is equal to 0. So the situation is like that. We have known boundary condition to the right. So we have essentially known solution here, and we don't know what is happening here in this part. But whatever we do, if you use the integrating factor, we arrive at the same integral differential equation as before. So you can see that, for me, it is a beauty power of mathematics. You know, we have several very different models coming from chemical engineering, essentially. And by, in some sense, systematic transformation of variables, we make all these problems the same, practically one problem. The problem W sub t is equal to a parameter times the antiderivative of unknown times the exponential function. Okay. And actually, these equations look still quite unpleasant, but they are really not. Because if you look if you get rid of unnecessary parameters and so on, essentially everything boils down to the system, to the equation 23, where here you have either antiderivative from 0 to psi or from psi, x here, to infinity of an object of this type. In all our applications, phi is the exponential function. But the theory which I present you here can be exactly in the same way developed if phi is an arbitrary entire function of exponential type of some sort. But the problem is now, let us go now from engineering to some analysis, some functional analysis. This is essentially an it is an differential operator equation. To be able to do something sensible, we must assume that this operator, J plus minus, act in some sensible space. So at this moment, we assume that we have some space X plus minus is a space of L1 type. It turns out that some exponential weights are necessary here, and we assume that our operators J plus minus are bounded in this space. And then if you take into account the formula, which tells you that iterates of antiderivative can be expressed as antiderivative of a convolution of function times the kernel y minus x to a certain power. By the way, I mean, this expression is now extremely popular because it is used in millions of papers on fractional derivatives. But we are talking about regular derivatives, so this is the formula. Joining or combining nth power of antiderivative with the antiderivative of certain convolution, certain product actually. And then if you simply do calculations and use the fact that your function phi here is a nice entire function, then we convert our problem to a very simple non-autonomous operator, differential operator equation 26. But the fact that it is non-autonomous problem doesn't make our life too difficult, because all operators here, so independent of these operators, commute. The problem, if you have a non-autonomous problem of, let us say, of general type. Sorry, okay. If you consider a non-autonomous problem with arbitrary family of operators A, then in general, U is not equal to, so you cannot use the trick from the scalar case. No. And the reason for this is that AS not necessarily commute, so you cannot really differentiate the exponent. But if these operators here commute, and this is the case of in the equation 26, then the solution of this problem is precisely given by this formula. And then we can simply write down the solution in the explicit form as identity plus minus tj plus minus to the power plus minus m. This can be justified by Danforth calculus, provided, of course, that you don't have problems with spectrum containing singular points of the functions you use. And this is the case here. For case plus here, everything is fine. So this formula in this case gives the global solution. If you have minus here, then the solution is local, because then we have the cut. We have to consider the cut from 1 to plus infinity, and unfortunately, one is the singularity of this. So we cannot actually get close enough to the singularity here. So all these problems essentially boils down to finding operators given by this explicit formula. Just to conclude, again, sometimes even in a functional analyst has to get his hands or her hands dirty, but in the process actually we discovered a number of identities for special functions which we couldn't find in Rzyk, Gradstein, or Abramowitz and Stegun or whatever. So actually it's quite interesting. So in the case when we have linear growth and decay rate, everything is can be calculated fully. So for example, if we consider equation with growth, so alpha is equal to 1 of this form, then the solution, this intermediate solution W, which is the solution of this operator equation, differential operator equation is given by, I haven't actually calculated this here. So the solution of W in this case is given simply by this formula. And then if you take backward substitution, you obtain formula like that, as easy as this. I told you at the beginning that pure fragmentation equations display very peculiar behaviors called shattering, so the loss of mass. The same happens in the case of fragmentation with growth or decay. Just to remind you that M1 is the total mass of the system. Standard calculations show that the mass of the total system should grow or decay according to the formula, this formula here. So exponentially should exponentially grow or exponentially decay. However, if you use our explicit solution to the problem and calculate the first moment, so we calculate the mass, then you can see easily that this is the theoretical growth on decay, but it is actually also multiplied by factors which show that there is a mass loss in each case. So the total mass doesn't follow the theoretical formula for mass or loss growth. Okay, so I have a few minutes more. Okay, so these are pictures, but probably they are too busy. Let me conclude the talk with the case of constant growth rate. This is a case in which we have an operator differential equation of the type we know very well, but unfortunately, we have to make sure that the solution satisfies this additional condition along the, let us say, diagonal to the left. So essentially, we are solving this equation for arbitrary psi belonging to R, and we will be looking, sorry, for a part of the initial condition. So this part psi, which will ensure that this equation is satisfied. Let me skip calculations. So as before, the global solution of the problem is given simply by this formula 32. So it's identity plus t times antiderivative, and this operator taken to the power m. And here phi is defined on the whole space R, on the whole line R. Now, the problem is that this is a non-local operator, so we cannot simply split this into positive and negative part. So we use again Danforth integral representation for the solution. And here we will be able to split this because if we do it carefully, we will see that for psi bigger than 0, the initial condition phi is known. It is our original initial condition of the problem. So if psi here is bigger than 0, then this formula gives us the solution, the full solution. However, if we take psi smaller than 0, then unfortunately here we will have a term running from something which is smaller than 0 to infinity, which will then encompass a part which we know and the part which we don't know. So this part we have to split. And in this case, we split this part into the integral from 0 to infinity and from psi to 0. This part is unknown for psi smaller than 0. This part is known, but it is no longer simply the solution for psi bigger than 0. It is just some known function. And if we introduce now also the resolver. I mean, so if we introduce the antiderivative of this fancy type with psi smaller than 0, then we can convert our problem by splitting this into I plus t to the tj to the power m on the unknown initial condition, evaluated at this value t equal to minus b minus 1 psi. Just remember that this is not a local operation, so I cannot simply substitute t here. I have actually to make an expansion. And then on the other side, I have a known function f. Okay. For arbitrary m, this operator is difficult to handle. It is related to this confluent hypergeometric function, Kummer hypergeometric function. But if we assume that m is an integer, then we can simply make a binomial expansion here, and we can convert this problem into a differential equation, let us say, jumping a few steps, differential equation 37. It is a very unpleasant differential equation because it's, again, non-autonomous differential equation. So this is, it has some symmetry here. And I mean, sometimes miracles happen. And in my opinion, a miracle has happened here, that if you use transformation, this is the only transformation you can use here. Namely, if you change z into e to the power minus zeta squared over 2, so Gaussian, essentially, times y will be the new function. This will transform 37 into a constant coefficient equation, a polynomial, precisely speaking, Hermite polynomial. Probabilistic Hermite polynomial of order m is equal to this. So we were able to transform very general and very unpleasant ODE, higher order non-autonomous ODE into something, into constant coefficient equation, which essentially can be solved by quadratures. And it is also quite interesting. I haven't heard, you know, this my Russian colleague told me this. I didn't believe him. I proved this fact. But essentially, this equation, as I said earlier, can be solved in quadratures. So if you find simple real roots of the Hermite polynomial, then using the Wronskian, nobody teaches Wronskian anymore, but in the case when you have, when your equation, constant coefficient equation here, not necessarily related to Hermite polynomial, if this constant coefficient higher order equation has simple roots, in Wronskian almost everything simplifies. And essentially in this case, you obtain, in place of these determinants which are in Wronskian, we essentially obtain the derivative of the polynomial evaluated at the roots of the polynomial, of this polynomial. Okay, so in this way, if you see, I don't know, okay, this is probably, I will be finishing, don't bother. So essentially what happens is that at the end, the unique solution of our problem, so this initial condition, unknown initial condition, is given simply by respective derivative of the solution of the Hermite polynomial equation 38. And therefore, in some sense, the whole problem is solved in quadratures. So probably with this, I will finish. And thank you very much for your attention.
Thank you for your talk. Any question? Rather, Agnes, please. No.
I was just clapping the hand.
Okay. So, any questions? Ryszard Rudnicki, please.
Okay. It is not a question, but rather a remark. If you consider fragmentation coagulation equations with power function, then sometimes it is possible to, first of all, to find equations, ordinary differential equations for moments, and then solve these equations, and in this way you obtain moments. If you know that these numbers are moments of some distribution, but it should be in the case when you have some preservation of mass, for example, then you are able to find, say, explicit, in some sense, explicit formula. You should transfer moments to the distributions as possible to go by this direction.
But no, I know this. The problem is that, I mean, in general, I think the question. This is the moment problem, yes. Yeah. So whether you can, I mean, the problem has theoretically solution. We know that if we know all moments of the problem, then you can theoretically retrieve the distribution. But in cases, I mean, in some cases here it could be possible, but it is not an easy problem.
No, I do not claim. I do not claim that it's possible to do. In case, it's
what we quite often do. We use non-inequalities for moments actually to prove global solvability. But I mean, as I say, this is to a certain extent a game. You know, we simply took an old paper by Ziff, and to write, something for his birthday, we decided to try to extend the results, and I mean, something unexpected happened. That it worked, for a large class of equations.
And the second solution, possible solution, as I said, I do not claim that I will be able to solve this problem, is to take some probabilistic interpretation of these equations. And sometimes it's possible to write the solution, I mean, that the densities which describe the evolution of fragmentation coagulation equation as some stochastic process. It is possible. Sometimes it's possible.
Yeah, I mean, in one or more actually of his papers, Ziff was doing argument like that and arriving essentially at the. I mean, Kummer distribution is I think known in probability, so it is related to this. But you know me long enough to know that I if I see any probability, I go long and difficult route to avoid it. So, so yeah.
Another question? Comments? Okay. If not, so thank you again.
Thanks.
And thank you very much. And I think that now we have time for networking and informal discussions. Thank you.